Hi, my name is Walker Reed, and this is Lab 6 Magnetic Molasses. So for an introduction for this lab, the purpose was to collect data of a bar magnet following through a tube of aluminum foil and measure how long it takes in order to observe Faraday's law. So some fundamental concepts that were involved with this lab are Faraday's law, which says EMF is equal to negative d phi over dt, the Biot-Savart law, which is shown there, Newton's second and third laws, mainly F is equal to ma, Ohm's law, magnetic force on a loop, and then the time derivative of magnetic flux. Some overview of the results found: the experimental time that we calculated for it to fall through the tube was 0.482 seconds, and the computational time was 0.354 seconds. Here's a picture of the experimental setup. So the system is the aluminum foil and the magnet, and the surroundings are everything else. First, I had to find the north and south pole of the magnet using a magnetometer on our phone, and then we dropped the magnet in and recorded the time it took to pass through 5 different times. So here's a picture of the setup with the aluminum foil and the magnet. The average for those times came out to 0.482 seconds. And there's the actual video. So the length of the tube we found to be 0.29 meters, which was given to us on like the box for the aluminum foil. The width of the foil was 0.004 meters. The inner radius was 0.024 meters. The mass we estimated at 0.091 kilograms, and our mu value that was calculated in lab 4 was 5.295. So here's the code that was involved. On the right side we have the physical constants, so the resistivity, the G value, we have the length of the tube, the width that we estimated, inner radius, and then the rest of the given values. On the left side, that's where we filled in the mass and what the mu that I showed on the last slide was, and then the initial condition at t equals 0 and the velocity being 0, obviously. And then in the bottom left, you can see that we use the Biot-Savart law as shown in the first slide to calculate the magnetic field. For the next parts of the code, on the right side, you can see that we had to do a function to calculate the flux, which again, we're kind of using that formula that was shown at the beginning, the time derivative for magnetic flux. And then on the left side, we're calculating the B field and then finding the F net using the F grab and F magnetic, as well as using Newton's second law there with the velocity update formula. Here's the output that that code created. So you can see the velocity versus time graph given, and it outputs the amount of time that it took for the magnet to fall through the length of the aluminum tube. So in conclusion, some potential errors that could have arisen from the experiment was that we did not have a scale to get the correct mass or weight of the magnet, which could have led to the different times among the computational and experimental values. We also didn't have a ruler that measured the exact radius and thickness of the aluminum foil, so it was kind of a guesstimation, kind of using like online sources. For the what if questions, the first one is what if the resistivity of the conductor were reduced as close as possible to 0, and how would the dynamics of the falling magnet change? So if the resistance was reduced towards 0, then it would obviously increase the current using Ohm's law and leading to a more powerful magnetic field, therefore slowing down the magnet even more. And then if holes or slots were cut into the tube, this would lead to less ring currents in the tube, therefore producing a smaller magnetic field acting upon the magnet, and that would lead to a faster time that the magnet would fall through the tube.